Thank you everyone for joining this Archimedeans talk. We're extremely lucky to be joined by Professor Kutyniok this evening, who plans to talk to us about the future of maths in the age of artificial intelligence. Professor Kutyniok is a Bavarian AI chair in the Institute of Mathematics at the Ludwig Maximilian University of Munich. She is a Simmons Fellow here at the Isaac Newton Institute, and just a month ago, upon invitation, gave a series of lectures to the London Mathematical Society on mathematics of machine learning. She's also been elected to be Vice President for the Society for Industrial and Applied Mathematics and holds many more positions and awards. And with that, I'll pass on to Professor Kutyniok.
Yeah, thank you so much for the very nice introduction, and also thank you so much for the invitation. It's really a great pleasure and also honor for me to give a talk here. Now, I think we all know how tremendously successful artificial intelligence is, and in this talk, I would like to discuss a bit what the role of mathematics is currently and also what it will be in the future. So if you look closer into this talk, we will focus also mainly on deep learning as one key method of artificial intelligence. What one observes is that these methods have a tremendous impact on public life. So for instance, autonomous driving, speech recognition, also legal issues where things concerning social decisioning are decided already by AI-based approaches. And then, the whole healthcare sector, which, as we know, is tremendously important. In particular now, the last years showed it even very prominently. Then if we get a bit closer to mathematics, we already observe that artificial intelligence methods have as well as tremendous impact on science. So here, this went through the news, for instance, where there was a breakthrough in a certain sense concerning protein folding by such types of algorithms. And you see here this new algorithms, AlphaFold and AlphaFold 2, what a significant improvement it made. Then if we get to mathematics itself, we observe that from, let's say, 2012 on, there was a tremendous impact first on the area of imaging sciences inverse problems. And so here, you see a list of several problems in the area of imaging sciences which people aim to solve, like denoising, classification, in-painting, recovering of missing data, and so on. The area of the impact on numerical analysis of partial differential equations was much later. But now also there, there's a strong increase on publications in that direction. So why? The reason is that in imaging sciences, for an image, there is no rigorous physical model. So, learning methods make a lot of sense. Sorry. But for partial differential equations, you can ask why you need a learning algorithm, because a PDE is a physical model itself. So there's not much to learn. But what turned out is that in the high dimensional regime, these methods are extremely efficient and also often can circumvent the so-called curse of dimensionality. And so therefore, their artificial intelligence is typically used in a very high dimensional regime. But then there is also another side, although everything looks so bright, what I just said, there was an incident some years ago at one of the big AI conferences where a researcher from actually Google AI, Ali Rahimi, received a prestigious award, and in his plenary talk, he claimed that at that time, machine learning and also artificial intelligence is to a certain extent still alchemy. And this is also, well, to a certain extent still true today. So what he said was that researchers do not know why some algorithms work and others don't, nor do they have rigorous criteria for choosing one AI architecture over another. So it's a lot of trial and error which happens there. And then if we look even closer, we observe that there are also tremendous problems with these methods, for instance, concerning trustworthiness. Yeah, so here in BBC News, there was an article which said computers can be made to see a sea turtle as a gun or hear a concerto as someone's voice. And then there are a lot of other examples, for instance, concerning self-driving cars, which certainly react to traffic signs, but if you put stickers on them in a particular manner, then you can fool these cars and they make a completely wrong decision. And that there are, many problems was also nicely discussed in this article by Michael Elat from the Technion, or in 2000, 17. So he called it Deep Trouble, Deep Learning's Impact on Image Processing, Mathematics, and Humanity. And in this article, he talks about that now we have these powerful methods, but we don't have any theoretical foundation for those. And also, I mean, sometimes they cause problems which we cannot predict. So from my perspective, therefore, in this whole area, there are two key challenges for mathematics. One is mathematics for deep learning, or more general for artificial intelligence. And this asks for, can we derive a deep mathematical understanding? Can we use mathematics to make those methods more robust, for instance? Can we explain the outcome? On the other hand, we have deep learning or general artificial intelligence for mathematics, meaning for mathematical problems. So for instance, imaging sciences. Can I use these approaches now to solve problems from the area of imaging sciences? Can I use these methods now to solve problems from the area of numerical analysis of PDEs? Yeah, so there are these two directions, and in those, I mean, I would like to show you a couple of examples to discuss with you maybe some recent progress and where things can go. But before doing that, I would like to give you a gentle introduction into deep neural networks, which will be the heart of this talk, so that you see where things come from and how they are rigorously defined. So everything started around 1943 with McParlock and Pitts, and what they aimed to do was they aimed to, well, I mean, introduce artificial intelligence and algorithmic approach to learning, and their approach was quite smart. Certainly humans, or we believe at least humans, are quite intelligent. So what they aim to do is they aim to mimic the functionality of the human brain. Now the human brain consists of neurons. And so what they did was they mimicked an artificial neuron, or introduced an artificial neuron, which they then connected to an artificial neural network. Okay, so let's take a closer look. This is a neuron. So what happens here is you get signals coming in. These signals you call x1, x2, x3, and so on. Then in these dendrites, these signals can be amplified. And so this is mimicked by these weights. So what comes here with x1 times w1, x1, x2 times w2, and so on. Then here in the soma, everything is accumulated. This happens here through the sum. So what you get here is a sum xi wi. Now the neuron has to decide whether to fire or not, and it does that by a threshold, a bias b. And so if the sum is greater than b, then it fires a 1. If it's less or equal than b, it fires a 0, meaning it doesn't fire at all. Yeah, so this is a very, very simplified mathematical model of a neuron. And we will later on connect such artificial neurons, and the free parameters will be these weights and the biases. So these we will then modify during the learning process. Okay, so now let's look at the precise mathematical definition of an artificial neuron, and then also it seems that this is quite simplistic, so we may make this also a little more complicated to a certain extent. Okay, so this is an artificial neuron. We have our weights, we have the biases, and now instead of just having 0 or 1 here, we choose now an activation function which we apply to this sum minus b. And so this is now the definition of an artificial neuron. You see it's very easy. We have here an affine linear function, and then we have this activation function. Now, in the previous slide, our activation function had a special form. Namely, it could be 1 or 0. So this was the Heaviside function on the previous slide. But you can certainly also choose something more smooth, which could be the sigmoidal function. But what people use these days almost always is so-called rectifiable linear unit, which is the max of 0 and x. Yeah, so it's a function which is just 0 and then x. This looks very simple. I mean, it's a very simple spline function, but for all practical purposes, this seems to be sufficient. Okay, so now we take these artificial neurons, we build a neural network. So let's again look at an example first. So these yellow dots are artificial neurons. You see something incoming here, something outgoing here, something incoming here, outgoing, and so on. And so you can write this in a formula of this type. So let's see how this connects to this graph. So this is my input x, x1, x2, x3. Then I first need to mimic or encode these connections. This I do by this matrix W1. And you see how it goes. The first output is this weight times x1 plus this weight times x2, which are these two connections. Then the second output is this weight times x3, which is this connection. And the third output is this weight times x3, which is this connection. Then, as you see here, the bias term is added component-wise and also the activation function. Yeah, and this gives me this part, and now we keep going. So the next connections are now encoded by this matrix, which goes from R3 to R2. Again, I add the bias term here, and well, then I stop in this little example, otherwise I would get the next activation function and so on and so on. Yeah, so this way, I mean, concatenating artificial neurons leads to a composition of affine linear maps and activation functions. And so, maybe not that surprisingly, this is the definition of a neural network. You see here the composition of these affine linear functions and activation functions, and the activation function, like on the previous slides, are univariate, so they go from R to R, and typically non-linear, because otherwise you would just have a linear function, an affine linear function. And also of importance is the number of layers, which connects to the number of affine linear functions. Okay, so that's a neural network. It's a function from RD to some RNL, maybe NL often equal to 1. So what do you do with a neural network? You learn complicated functions from which you just have sample values. So let's assume I have a complicated function defined on a lower dimension manifold, maybe with a finite output. Now, so let's say as an example, I have images of cats and images of dogs. And so maybe the dogs I map to 1 and the cats I map to 2. But what I have at hand, so this is usually images are on a lower dimensional manifold. Now, what I have at hand are just sample values. I have images of cats with the value 1 and images of dogs with the value 2. So now these samples from these I want to learn F. And first I split the samples into a training and a test data set. The training I use for training, the test I set aside. Then I need to decide which architecture to choose, because now I choose a neural network which will then approximate my F. So I need to choose a lot of things. I need to choose how many layers I take, how many neurons in each layer, which activation function. Maybe I pre-select certain entries of these weights to be set equal to 0, to not have a fully connected network in the beginning. Then once I've decided that, I have my model. And now I need to choose my free parameters, the weights and the biases. So this I do through an optimization problem. So now I learn these weight matrices and these bias vectors. And I do this in the following way. So please first take a look here. This is my neural network function, which I apply to these xi's, the samples I know. And I would like certainly that this is close to f of xi, because I want to approximate it. The closeness is given by a loss function. So this would be the square loss. I take the difference squared. And then if I want, I can also incorporate additional properties of the weights and the biases through a regularization term, but this is often also not used. So in that sense, you now have to solve this minimization problem. And then once you've done that, you will get, so you have then the weight matrices and the bias terms, and this will give you a fixed function. The optimization problem is usually solved using stochastic gradient descent. You might know gradient descent, but gradient descent cannot be used because then, since the number of training samples is usually in the millions, you would need to compute 1 million gradients each time. That's much too cumbersome. So therefore, we randomly select certain samples and then just compute the gradient for those. So then you get your neural network function, and you hope that that is close to f, what you want to learn, and you check whether this is close by now using the test data set. You put in the xi's from the test data set and hope it's close to f of xi. Okay, so This is the procedure of a training phase for a neural network, and this works extremely well. Why does it work extremely well now? Because, as we saw, everything started in 1943. Now, we have two advantages now. First of all, I mean, we have networks with hundreds of layers. So you can train really deep neural networks. That seems to make a huge difference. And secondly, the age of data started. So we have a huge amount of training data. And also that, so for instance, just go on the internet and download images. You can download 1 million images and then train the neural network on that. So these are the main two aspects why now neural networks work that well. But there are still a lot of mysteries. So what is, for instance, one mystery? One mystery is this, what's called overfitting. So what is that? Now let's assume you have two data sets here. Let's say your blue dots are the cats and the green dots are the cats and the blue stars are the dogs. And you would like to separate those. If your neural network doesn't have that much flexibility, you can just draw lines and you will never be able to get a clean separation. If your neural network has a bit more parameters, maybe you can draw a boundary like this. And this seems to be very good because this might be here an outlier, wrongly classified. But then if the network has too much flexibilities, maybe you could get something like this. And this could be a problem because you see, I mean, if this is an outlier, then if you get a new blue star, you might misclassify it because it ends up in the wrong group. And so this is overfitting. The network has too much flexibility and it aims to do the good job too good. But for some reason, neural networks do not run into this risk, although they are highly over-parameterized. They have a huge amount of parameters in the millions. And so this you can also see here, this phenomenon. This is what classical statistical learning theory tells you. You have the size of the hypothesis class, so here are the neural networks, the size of the neural networks, you have the error. The training error, as you increase the size of the neural network, will certainly go down because you have more flexibility to fit your training data. But the test error, so in the end, once you trained it, the test error then goes up again at some point. And this is this phenomena of overfitting. You have this sweet spot, and after that, if you take too many parameters, you do worse. But for some reason, with today's neural networks, you do not run into this risk. Namely, at one point, you see the left-hand side coincides with this picture, but now if you increase the networks more and more, then the test error goes down again. And that's the so-called double descent curve, which is not fully explained yet. Another phenomenon is, so therefore, I mean, practitioners say, if you want to choose a neural network, choose the largest which fits in your GPU. So the other mystery, or one other mystery, is stochastic gradient descent. Why does it work that well? Gradient descent, what does it do? It starts somewhere, it walks down the hill, and it ends up in a minimum, a local or a global minimum. With stochastic gradient descent, you start somewhere, then you do this erratic path down the mountain, and you might end up in a very different minimum. And then when you think about what you optimize over a landscape of this type, then you are really wondering why stochastic gradient descent always finds that good local minima. So that's another surprising phenomenon. Okay, so what are now the main areas of mathematics for deep learning? Remember what we first did? We chose the architecture. That's expressivity. So which aspects of a neural network architecture affects the performance? How do I choose that best? And mathematical areas are particular approximation theory. Next, we train our neural network. So this goes to optimization, optimal control, also geometric methods for analyzing landscape. So why does stochastic gradient descent work that well, although the problem is highly non-convex? Then the generalization problem. Why do large networks not overfit? What is the role of depth? Can we get bounds for generalization? Meaning, can we estimate the test, the error when we apply the test? So the test error, can we estimate the test error? And so this goes typically more in the statistical domain. So in fact, these three are the components of the error of a statistical learning problem. And there's another area which I also want to explicitly mention, which I find quite exciting, which is explainability. It's a different philosophy. So here you have a fixed neural network and you want to analyze, and it's already trained, you want to analyze how it works, how it reaches decisions, which features of my input data are important for my decision. Although this will not be the main part of this talk, but let me just spend 2 slides on that area because I think there's a lot of mathematics missing and it's a very exciting field. So the question is, I would like to understand decisions of black box predictors. So let's say I have a fixed neural network which classifies this as a 3. And so then I would like to know which pixels contribute most to the decision, and then my algorithm maybe outputs these red pixels contribute to the decision. And that seems to be also reasonable by the neural network because these openings indicate that this is indeed a 3. If the neural network, which classifies this maybe as an 8, then if I would like to have an explanation for it, maybe it would label these openings in blue because this plays against the decision that it's an 8. But there are a lot of open mathematical questions. What exactly is relevance? These relevance maps, which you see here in a mathematical sense. Can I talk about optimality? What about other modalities? And so what we did, we introduced an algorithm based on rate distortion theory, information theory, which shed a bit of light into that, but there's still a lot of open questions. Basically, there's almost none mathematics present. So in that sense, maybe as a vision, what you would like is in the end a decision indistinguishable from if you would talk to a human being. And let me show you one additional example to see how these explanations work in complicated environments. So here you have from telecommunication, these red dots are humans, these blue parts is a city map. And from each human, you have so each human has a cell phone and you know how good the reception is at this point. And this white point is the tower, the telecommunication tower. So then what the neural network does, it computes this black and white background, the so-called radio map, which indicates at each point how strong the signal there is. But then you might wonder why this black blob is here, because if you stand here, you stand right in front of the cell tower. The reception should be extremely good. So that doesn't make any sense. So then where are these explainability algorithms? You can find out that the network based this decision on these cell phone users, which actually have bad reception. And so in the end, we found out that there was actually a building missing here in the city. So this is another example. As I said, sometimes neural networks reach wrong decisions. And so here you see that if you do a bit smarter way with explainability methods, you can find out why to a certain extent. Yeah, so we now have a neural network which is trained and which classifies this as a diaper, which is obviously wrong. And if you look at classical methods like pixel-based methods, you get that these pixels are important for the decision, but there's no way you see why this was classified as a diaper. But then if you, let's say, do a bit more higher level explanations using so-called wavelets, then you see that, well, this seems to look a bit like a baby. So in that sense, the neural network has been maybe misguided and classified this as a diaper. The same here with a screw. There's obviously no screw in here, and classical explanation methods do not give something reasonable, but then these type of methods, so which we here called cartoon X, they indicate that this looks a bit like a screw, so that might have been a reason the network has been misguided. Or this might, let's say it that way, this might have been what the network has seen to reach that decision. Okay, so these are the four main areas of mathematics for deep learning for mathematics. There we have inverse problems. So in imaging sciences, asking maybe questions, can we combine this with classical methods? There are also a lot of methods going in there. And then partial differential equations, why do neural networks perform that well in high dimensional environments? And also their approaches like numerical mathematics. So now the first question we can ask is, are deep neural networks at least as good as all previous mathematical methods? And so the question is, and I mean, how can we check this? I mean, mathematical methods, the key ingredient for those are typically approximation tests. We approximate the solution. So it seems natural to ask, are neural networks as good approximators as all previous classical methods? And for this, I would like to take a short review of classical approximation theory and then show you what neural networks can do. So what is classical approximation theory in a nutshell? I mean, we have our class of functions which we want to approximate, let's say easy two functions, and we have a representation system, let's say an orthonormal basis. I don't know what your favorite orthonormal basis is. Then what classical approximation theory does to approximate an f is you're given a budget n. You can choose n elements of your system and you can build a linear combination to approximate f. And you do it in such a way that you best approximate f. That is a best n-term approximation. You make certain error, and this is the error of best n-term approximation. Then, if you let now n go to infinity and your phi i's are a complete system, this error will go to 0. And you can ask at which rate does it go to 0? What is the largest gamma? And so this is the approximation rate. It tells you how good your representation system is for approximating your class C. So this sets into relation the approximation accuracy with the complexity of the approximating system. In terms of sparsity, what you aim for are very sparse approximations, so with very few terms. Yeah, so you want to keep the complexity in that sense small, n small. Okay, so one example of this, not going maybe too much into the details, there's a class which is typically used for images or cartoon-like functions. They look like this. Yeah, so they have two areas in which they are smooth in C2, and then there's a C2 discontinuity curve. And there's also a result, also by Donohoe, which shows that under certain conditions, the error of best n-term approximation, the best decay we can get is n to the -1. Yeah, so that's the benchmark result. If we can now derive a system which achieves this rate, we can say it is an optimal system for this class of functions. Yeah? Okay, and so there are many choices. Maybe you've heard of wavelets, which is a system which is built from a generating function. It moves around on the plane and it has a zooming factor, a scale. But these wavelets can only achieve a rate of n to the -1. And so there were several suggestions how you can improve that, because wavelets are like a little square, and it would be much better to have elements to approximate which are themselves aligned. And so one possibility are shielded systems, which I also don't want to go into the details. I mean, they are systems which basically look like this. They have a more complicated scaling matrix, so you can zoom in a more complicated manner. You have something to change their orientation, and so you can build a system of this type. Again, not going too much into the details, but in any case with these shieldeds, you can show that the error which you make for these cartoon-like functions have this magical decay rate n to the -1 up to a log factor. Yeah, so they are almost optimal or optimal up to a log factor. And so if you're interested in that, I mean, we have an extensive software library, shielded.org, so a lot of demos, and where you can try out things in a lot of different languages. Okay. So we saw this slide already, so this gives a bit of meat to the slide. We saw this example of a class of cartoon-like functions and shielded systems. And that gave us the optimal rate. Okay, so let's go to deep neural networks now. Again, this is copied from a previous slide. That's the definition of a neural network, which we already saw. So what we first need is a notion for complexity, because if you want to transfer results, before our complexity was this sparsity, we can certainly not use this here. So what we measure here as complexity is concerning how much storage I need. And so the way I measure it, I measure how many non-zeros there are in the weight matrices and the bias terms. Now, so this 0, it's not a norm, but it indicates you just count the number of non-zero entries. And so this is related to memory efficiency. And we will also use this expression, but I will recall it at that point again. So what we now want to measure is, or set into relation, is the approximation accuracy as related to the complexity of the approximating neural network, but now in terms of memory efficiency, which is now our measure for complexity. Yeah? So we want to construct networks which have, in a sense, optimal approximation properties, but which are small concerning their complexity. Okay, so there's a very classical result. You see, it's a very old result concerning approximation, which is the universal approximation theory. So what does it say? It says something very interesting. It says if I have a continuous function on a compact domain, and then I have an activation function, which is, yeah, continuous, not a polynomial. So then for every accuracy, yeah, so I have here my function continuous on a compact domain. For every accuracy, I can find a function of this type which approximates that f with that accuracy. Now, what are those functions? These functions are networks which look like this. You see this here. I mean, this first affine linear function encodes these connections. Then I have my activation function, and then I sum everything up, which are these connections. Okay, so every continuous function on a compact domain can be approximated with arbitrary accuracy by a shallow neural network. So that's quite powerful. But I mean, the complexity can be arbitrarily large. There's no bound on the number on n here, which is and how many connections you have. That result doesn't tell me anything about that, about the complexity. There are a lot of other results. For instance, I mean, Jarodsky has beautiful results for instance, also other function classes, S times continuously differentiable functions. Here now with a very special activation function, the ReLU. And then there exist neural networks he showed with this approximation, and you see here now the complexity shows up precisely. Now, so here the accuracy is exactly measured already by the complexity of the approximating neural network. So that's already taking that into account, the complexity. But here, I mean, this result is not optimal. So how to go about that? What we need is a lower bound for the complexity. How many connections do we definitely need? And so one possibility is this result, which we derived, which says the following. We first define a very abstract learning procedure. And what does a learning procedure consist of? Well, we have our model class of functions again, like we had many times, maybe cartoon-like functions. The learning algorithm then will take one of these functions, maybe take samples values just of it. It will have an accuracy, and then it computes a neural network which approximates this function with that accuracy. So that's what a high-level learning algorithm does. And then one can show that for these neural networks which are learned, the complexity of those behaves in a very special way. Namely, this product, epsilon to gamma times this complexity, converts to infinity. And you see that's, well, in a sense, an interesting result, because as you let epsilon, the accuracy go to 0, this will go to 0. For the product to go to infinity, this has to go to infinity faster than epsilon to gamma goes to 0. So this gives me a lower bound on the complexity. And so now I can ask, can this lower bound be met? And also what happens in this limit case? Now, not going too much into details, you can actually show and construct systems exactly which meet this lower bound. And what you do for that is, I think, quite interesting. You basically transfer everything from the approximation world to the neural network world. So you consider a representation system with an optimal approximation rate. So for instance, shearlets. You realize then every element by a neural network. Remember, neural network are just functions. So you take every shearlet, you build a little neural network, which gives me the same function. And then you build such an end-term approximation also by networks. So how do you do that? Well, you have all your elements like your shearlets, you connect them, and you sum that up. So this network is a sum, a weighted sum of these elements. Okay, and once you've done everything, I mean, then you can get results of this type. So for every accuracy and for any cartoon-like function, I find a neural network with complexity O of n, so that the error behaves like this optimal rate. Yeah, so this shows that indeed you can reach the optimal approximation rate, but at the same time with networks which have very low complexity. Yeah, so as a higher level result, in general, one can show that deep neural networks achieve optimal approximation properties actually of all such systems, wavelets, shearlets, and all these systems, so-called affine systems combined. So it is at least as good as all those systems we worked on for a long time. And also something more interesting happens, because now you can ask, now I take this architecture and I train it. And in the proof, I put shearlets here, for instance, or wavelets. But now what happens if I just let the network have its freedom and I just train it? What will it learn in these compartments? And what happens is quite interesting. So if we just have a linear singularity, then I train my neural network, then these compartments, you will get structures of this type, so-called ridgelets. And if you train your neural network on something a bit more complicated, then you will get functions of this type, so-called, well, I mean, they are close to shearlets. So in that sense, in these compartments, if I let the network have its freedom, it still learns something similar to what we introduced before in classical approximation theory. So which is, I think, quite intriguing. Okay, so now you can ask, are deep neural networks really better than classical methods? For this, I would like to take you now on a short tour to imaging sciences. Because there, I think you can see very clearly that neural networks have a huge advantage over classical methods. So this relates now to inverse problems. And so what is an inverse problem? So let's just take a look at this example. You have an image and I take out parts. And now I ask, given this image, can I reconstruct this image? Can I recover missing parts? So that's a very classical problem, recovering of missing data. The way I can make this mathematically precise, I can say there's an operator which maps this image to this image, so which takes out things. And then I want to invert the operator. Therefore, it's an inverse problem. And so you can phrase it this way. In the finite dimension situation, it's solving a linear system of equations. But this one can also put in a, let's say, Hilbert space setting. And there's a very classical method to solve those problems. Again, optimization methods. So you see that here you have given now the operator, you have given G, and you want to recover F. You want to basically invert K. And the way you can do that is by solving this minimization problem. What you see here is, this is the so-called data fidelity term. So if you minimize this, you aim to solve this inverse problem as accurately as possible. And then certainly, I mean, you would like to also incorporate properties of your solution. And we saw that, for instance, natural images have a sparse representation in, let's say, shearlets or also wavelets. And so this we now incorporate in this so-called penalty term, where we put here now, let's say, wavelets or shearlets, and we put then the L1 norm on, which indicates sparsity. So this is it's called sparse regularization. And a classical method to solve this. Now, combining this with deep learning approaches, there are various ways to do that. One can, for instance, look at this algorithm itself. It can be solved by so-called ADMM, not going into the details, but this has a denoising step. It's an iterative algorithm. It has a denoising step, and neural networks are really good in denoising. So you can just take this step out and replace it by a neural network. That's called plug and play with CNN denoising. Or you can replace a bit more complicated steps of this algorithm by neural networks. So you still have this overall structure, and then you replace parts. And so there are various other ways how do you combine classical solvers with deep neural networks. So let me show you one additional example, which comes from medical imaging, computed tomography. A CT scanner does the following. It computes line integrals through the human body, and each time it gives you a one-dimensional function, which is then one slice of this so-called sinogram, and then you rotate it. And that way you fill the sinogram. And so in mathematical terms, this is a radon transform. You have your F here, and you compute line integrals with various angles and various offsets. So now the task is from this to recover the interior of the human body. And this becomes really hard if you not have the full scan. So if you cannot rotate by 180 degrees, but only by parts, because then you have a whole chunk of data missing. And so then the question is, how from this partial data you can actually reconstruct. And you see that usually fails miserably. So for instance, if you have a 60-degree missing angle, this is my original image, then if I choose a crude reconstruction method, I get this. I have a huge amount of artifacts because I have this whole chunk of missing data. If I do a bit smarter job, like with this sparse regularization with shearlets, you get a better image, but still it's not great. You see all the problems here. Yeah, but then, you can get mathematically a bit more into that problem. So what you can, for instance, observe if you recover only parts and then you increase the angle where you recover, you see that already at a very early stage, you can recover very precisely edges with their direction. Yeah, so you can imagine if I just compute line integrals in these directions and then I recover, I will be able to recover these parts because at some point these line integrals are not zero and then they become zero, but these will be completely smeared out. So I have parts of the singularities together with the direction, depending on the directionality, and others which I cannot recover at all. And so there's a precise mathematical theory behind that, which is based on so-called wavefront sets, which are directions, singularities together with the direction. Shearlets are very good in identifying that and then putting things together. What you can derive is an approach like this. So we first solve just our sparse regularization problem. So you see here, you have here the operator, the radon transform, that's this data fidelity term, and then here the FDL1 norm of the shearlet coefficients. That gives you this crude reconstruction. But then what we do is we apply another shearlet transform to what you get out. And so these are now inner products again of F star with shearlets. Sometimes I get zero. Sometimes these inner products are already reliable and nearly perfect. So that way, by applying the shearlet transform anew, I can separate and identify which parts are already recovered and which are not. And then I take thus the ones which I cannot recover. So I've identified precisely where the classical algorithms fails. And only there I now use a neural network. Yeah? So now I train the neural network specifically to recover these, I might say, invisible coefficients. Yeah, and then I put everything together, the invisible ones with the visible ones with the invisible ones, bring everything back in the spatial domain, and then I get results of this type. We saw the top two images already. This is the crude reconstruction from a 60-degree missing angle. This was a very good classical reconstruction. This is a neural network, which we put on the entire image, which is already a bit better. But then if you join, let both worlds join and take the best out of both worlds, and in that sense also surgically apply a neural network only where it's needed, you get a significantly better result. Yeah, so in that sense, I think one can say that deep neural networks very often by far outperform classical methods, but only if they are smartly used and used in connection with physics or classical methods. Yeah, and so this is another example, which is a classical edge extractor. And also here you see this would be what a human would detect as edges. These are classical approaches. And with a neural network, you can get a much more precise edge structure, and also directionality indicates the direction of the edges. And this is also a combination of classical methods, here shearlets with neural networks. Okay, so this shows now inverse problems. So how much time do I still have? Maybe you could.
I still got over 10 minutes left.
10 minutes, okay, good. So we can also now ask, what about solving partial differential equations? So that's a very different area. How are neural networks used for that? And what is typically done is also, a straightforward approach. Yeah, so this is our PDE. We have here the solution U, we have the differential operator, we have the right-hand side. And what people typically do is they approximate the solution by a neural network. So that's my Ansatz function. And then I train my neural network using the differential operator in the loss function. And so then I get a neural network which gives me or approximates the solution. So and there's now a ton of literature in that direction. I just want to show you one specific result and a bit more higher level viewpoint, so that you get the flavor of it. So here, this is this goes in the direction of parametric PDEs, meaning now I have not just one PDE, but I have a whole family of PDEs. And so let's say this family is governed by the parameter y. Yeah, so everything depends on it. The right-hand side depends on it, the solution, and then the y might be also incorporated in a non-trivial way. And what one typically asks is, if I have a parameter, can I compute the solution? This I usually want to do many times, because these parameters could be design parameters, and each time I change my design, I want to each time compute the solution anew. The course of dimensionality is a problem there. So the question is, first of all, can we solve this map by a neural network? Can we approximate it by a neural network? And can it circumvent this curse of dimensionality? Yeah, so we bring everything in the finite domain first, let's say in a so-called high fidelity space. So D is really large, but it's finite. And this is now the finite dimensional version of it. Yeah. So again, we have our parameter and some RP. We want to compute now this finite dimensional version of the solution. And so, if we can manage to do that, we get a very flexible universal approach. And we can now ask questions like, does there exist a neural network at all which approximates my map? What complexity does it has? In particular, in terms of all these dimensions like P and capital D. And also maybe how does it perform numerically? Because you see, this first question is a question from expressivity. Does there exist a neural network? If you not tell me anything about the training procedure. And basically, you can show this, you can show that there exists a neural network and the dependence of the complexity is benign. So it does scale in a modest manner. It does beat the curse of dimensionality, but this result only tells you there exists a neural network. This is always the case for expressivity results. It doesn't tell you more. It doesn't tell you anything about what happens if you train a neural network. Certainly, it would be nice to have a result of this, but this is currently out of reach, but you can drive extensive numerical experiments, and that way then numerically, in a certain sense, confirm that also there you don't run into the cross of dimensionality. So let me, in the very last maybe 3-4 minutes, say also a word of caution. Because I mean, neural networks right now, I mean, look like, let's say, the magic box which solve all problems. But there are also problems with neural networks beyond what one sees, like these robustness issues. And this problem comes from the area of computability. So what do we do on a very, very basic level? If we train a neural network, we compute something on a certain type of machine, typically a digital machine, a computer. And so one can ask, are these problems computable at all from a computability viewpoint? Can it be computed on a digital machine? And typically a classical model are Turing machines. And what one can show is that, for instance, the solution of finite dimensional inverse problems is actually not computable, particularly not by a deep neural network. Yeah, so this is a serious issue, because then, I mean, you cannot construct or cannot derive any error bounds for it if you compute it on a digital machine. Yeah, so you can, I mean, even if theoretically you have great error bounds, but if you then compute it on a digital machine, these error bounds will most likely not hold. You can actually not check it because it's not computable. Yeah, so no algorithms exists which on digital hardware derives neural networks which approximates that for a given accuracy. In that sense, the output is not reliable, it doesn't give any guarantees. And so this could be that this is a reason why sometimes instabilities occur. Yeah, so this is a general barrier which one need to be aware of and cautious of. So this is a result which depends on the hardware one uses. So then the question is, what about other hardware? And there are a lot of exciting developments like neuromorphic computing, biocomputing, and so on. And so what one can then, I mean, as a first step, theoretically show is that indeed, if you extend your model in a certain sense, called Bloom-Schupf-Smale machine, then suddenly the solution of such a finite dimensional inverse problem is indeed computable. Yeah, so this points towards that one really needs better hardware where one can then also check these error bounds, which we know theoretically. For the other, I mean, we have theory, bounds from theory, but it is just not possible to check them. Okay, so let me finish with some final thoughts. From my perspective, deep learning shows impressive performance in real life applications, but theoretical foundation is to a certain extent still largely missing. There's a lot of mathematics required, new mathematics, very exciting. It concerns almost all areas of mathematics. And then we have these two directions, mathematics for deep learning from mathematics, where we touched upon these different research directions, expressivity, learning, generalization, expandability, and here inverse problems, partial differential equations. And for all of those, I showed you a bit of glimpse into what research does, what questions people are wondering about. And so there's a long list of different problems, which are basically copied from this paper, which gives a lengthy introduction into the modern mathematics of deep learning. And so from my perspective, I mean, particularly from mathematics, there are really exciting future perspectives in that area. And as I said, I mean, all areas are in a certain sense required. Even areas like algebraic geometry are nowadays used for tackling these problems. And with this, I'd like to conclude and thank you a lot for your attention.